I think we can get started. It's almost 4:30. We've changed your panel on you, so I'll introduce everybody briefly and give you a little bit of background. Again, if you haven't met me before today in this room, my name's Rick Wheeler, and I'm a manager at Red Hat of the kernel team that does file systems and storage. And what I wanted to do in this last session today, which is the last session of Collab, I think, for anyone, is introduce you all to some of the most active leaders of the file storage and memory management world. Not just the people here in the chair. Raise your hand if you're going to the summit Thursday and Friday. There are a lot of people in the audience, right? So around you, you can ask all kinds of questions as well. So what we do every year at LSF, what we call LSF MM now, because these memory management people made us pollute our name. It's nice and short. We get together and we kind of do strategic planning of what the hard problems are, what we're working on, and try to get some kind of technical sense. It's an invitation-only event. It's gotten a lot larger than it used to be. I think we started, how many years ago? 2007 to 6, with like 7, 10 people. I don't know. So we're up to, I think, 90 this year. So we're actually, I think, larger than the kernel summit. So with no further ado, I'm going to let everybody introduce themselves, starting with Martin, who's our fearless leader of this year's event.
All right. My name is Martin Peterson. I work for Oracle. I'm a storage architect in the Linux group, and I work on all things SCSI and BlockIO and Linux.
I am Mick van Riel. I work for Red Hat. I look for interesting-looking bugs that come in the kernel and work on those. Many of them end up being in the memory management area, but some other parts of the kernel as well.
I'm Dave Chinner. I work on XFS and anything else related to file systems that gets in my way. I work for Red Hat, and I tend to carry a big stick around to keep people in line.
Hi, I'm Trond Myklebust. It's now 16 years since I woke up to find that Alan Cox had slipped my name in as a maintainer of the Linux NFS client. In those years, I've sort of taken it from being a hobby while I was doing particle physics at CERN to being a full-time employee at NetApp.
Which one pays better, Trond?
NetApp by far. NetApp by far.
Yeah, that's the right answer. Yeah. Yeah, so one thing I want to make a note. I mean, this is the last session. I do hope people ask questions. There's a mic out here on the table. If you have a question, do speak up. I think we might still be being broadcast, so don't say anything on camera that you don't want your management to hear about back home. So I'm going to start. So again, I'd like each of our panelists here to start by, what do you think in your area? We're going to talk about this most interesting to you in the next couple of days at the LSF MM Summit. Start with Trond this time.
As far as I'm concerned, the most interesting topic that we're going to be discussing is the copy offload stuff. It's been 3.5 years now since I brought an intern to the LSF at was it San Diego?
San Jose, maybe?
San Jose, okay. No, sorry, it was Boston. It doesn't matter.
Yeah.
And
all hotel ballrooms look the same.
They do.
Yeah.
And we, that person had been working on a copy offload version for NFS, both client and server, which is still sort of languishing in my patch list. But in the meantime, we've actually finished the NFS protocol work in the ITF for it. And the only thing that's holding us back now is basically a system call interface in order to allow us to do it in a standardized way.
Was there somebody in the audience who had patches?
Yeah, I refreshed it to a modern kernel.
Yeah.
The most important thing that I think that I'm here to talk about is to do with actually memory management, with the memory reclaim and shrinkers. Even though I'm a file system person, that seems to be an area that has significantly impacted on performance for file systems for quite some time, and so the lack of anybody else doing anything about it, that fell to me. So there's been a bunch of work that I've done for performance reasons, and that's been picked up by another guy, Glauber. Is he here? No. For making MCGs, memory control groups, and shrinking them work properly in containerized systems. So there's a lot of overlap in what we're trying to do and trying to sort out how that goes together and fix up all the broken shrinkers that are out there.
On the memory management side, there are several big things going on, some of which you've already heard about because they've been going on for 5 years. But there are also a few new things going on. One of the big things that you may not have heard about, or you've probably used it yourself but not really thought about it a whole lot. If you've mined bitcoins or anything like that, you know that your CPU is no longer the fastest chip in your computer. And there are some movements underway to use various other chips in the system, whether it be your infinite band controller or a GPU or a specialized ASIC or anything like that, to run programs on. And in order to do that in a better way than is done currently, we have to dedicate a device to a program. The idea is to have your userland program can have some threads running on the CPU and some other threads running on a specialized device, all sharing the same address space. And we're starting to think about how can you make a system like that work, where part of your program runs on the CPU and part of your program runs on something else, which may have its own memory and somehow needs to be kept memory coherent in the same address space. That's going to be one of the big changes coming up.
We have a whole list of things to talk about in the I/O track the next couple of days. Copy offload being one of the topics. I/O hints, how we convey to the storage what it is we're doing so the storage can try to be smarter about the commands we send down. What else do we have going on? We have error handling problems. That's a recurring topic. I/O hints has been a recurring topic as well, just like copy. I guess many of these things take a while, both to get settled in the standards bodies and for us to finish the implementation. But we do have many open issues, I find, this year in the I/O track. And aside from the more storagey stuff, like we just heard here, the new flash and post-flash non-volatile memory technologies are starting to appear, and we need to come up with smart ways in which we can deal with them, either from a storage or from a memory interface perspective.
Any questions in the audience? Anybody have things, either from the attendees or general audience, who want to poke at us?
I was just grateful Dave didn't say right back.
Right back?
It's on the agenda.
It's on the agenda, and I'm there to make sure nobody breaks it.
Yeah. Yeah, and I will note, I mean, we've mentioned copy offload a couple of times, and copy offload is not just for NFS. It works for SCSI. It can work for local file systems. It could work for almost any part of the stack and software as well. So one of the ideas that, again, we've talked about forever is, what did we end up calling the system? Was it copy file? Copy file. So hopefully we'll have a brand new system call. Like shipping next week, right? Monday.
I had it 10 years ago.
10 years ago. Yeah, and in summary, what it'll let you do, if it's not, some of us have been talking about it too long, but it lets you send a command to, say, a NetApp filer, in Trond's case, say, make a copy of file A called copy B, effectively, and B won't bring the data over the wire and back again. Just kind of cool. You want to comment on that?
Yeah, sure.
Defend yourself?
Well, the other thing that's important about it is that it allows the storage unit to do the copy in the most efficient way available to it. So, for instance, if you have, say, a Butterfs file system, then instead of doing a full copy, it might choose to do a reflink, basically a copy on write snapshot of the file, thus making it more or less a no-op and making the storage more efficient.
Okay, that's good. So I'm going to ask a mean question. So I'll start with Dave. So Dave, why, when is Butterfest going to be done as the world's leading?
That's a bit of a leading question, isn't it? The question is, when is Butterfest going to be done? Well, if anybody's seen a talk that I gave about a year and a half ago, I sort of said that Butterfest wasn't ready for production systems because it's not ready for production systems. Have I changed my opinion in the past 18 months or so? To tell you the truth, no. But on the other hand, there's still a lot of active work being done in Butterfest. There's still a lot of little bits and pieces, the polish that needs to be done on it. The core is much more stable than it was, but what matters when you're talking about storage is that it's bulletproof and reliable. Losing someone's data is losing one person's data too many. And when you talk about, it's not my data that matters, it's your data, and I'm responsible for making sure I don't lose your data. So when you look at it from that perspective, anything that loses data with alarming regularity, in my opinion, is not ready for production systems. And unfortunately, I do see that a little bit too often with Butterfest to change my opinion at this point in time.
So when will XFS be ready for production use?
So the question is, when will XFS be ready for production usage? Maybe in about another 20 years.
Just out of curiosity, how many people in the audience use Butterfest? How many people use ext2? Shame on you. Move forward. XFS? Yeah. Yeah. It's funny, there have been, I think last year was the only time I remember that we had XFS developers outnumbering ext4 developers and Butterfest developers in one room at one time. It was a freak of nature. It happened once. But there is, to your point, there's actually quite active communities in a lot of local file systems. Butterfest people, raise your hand who work in Butterfest. Ming, you're others. There are people kind of working. No need to be shame, Zach. ext4, ext3 developers? Yeah, so you see around you, you can find people to blame for all your woes right here.
We'll be over there later on if you want to beat us up.
Yeah. So one.
Your turn next.
Yeah. So I'm going to ask Rick a question. So Rick, what's good about having file system storage people come in and ruin your day as a memory management guy in 2 days? So what good comes out of having us all together?
A lot of the memory management stuff that goes on really has to do with the interaction between memory management file system and the I/O layer. Because the data starts out in memory and has to be written to disk. That bit is obvious. And there might be some checksumming going on at the same time. But also at the same time, the application might be writing new data to your just checksummed page. And suddenly the checksum is messed up. Things like that. So there are all kinds of little interactions going on between memory management and the I/O layer and the file system layer. And actually a lot of the sessions at LSF are shared between all three groups because they're just stuff in the interaction between the three subsystems that needs to be sorted out.
Okay. A question for Martin. So Martin, how close are we to getting that 5 million IOs per second all the way through the stack?
Using which technology?
All of them.
All of them. Yeah.
Well, so we have the advantage compared to some other operating systems that we have. It's both a blessing and a disadvantage. We have an I/O stack in place that is fairly flexible, and it allows us to hook things in various places. So the answer is, if we're doing 5 million IOPS on SCSI, then there's a lot of code in between the application submitting the I/O and until it hits the hardware. Whereas if we hook the I/O driver in higher up in the stack, for instance. There are some SSD vendors that do that. Then we have a much better chance. And it's not that the code we have in the rest of the I/O stack is bad, but devices have different needs and different characteristics, and inevitably we will need to have code in place to handle all of them.
Okay, and James, you want to introduce yourself just briefly?
Sorry, everybody. I always told you I had a board
You know,
meeting
I know.
commitment, so I actually left them after the last vote. They're still in there. So I'm James Bottomley. I'm the SCSI subsystem maintainer. I have to point out to Martin that if he's doing 5 million IOPS with a SCSI stack, it probably isn't mine then. Is that it?
Yeah, that's it. And, well, what do you look forward to? I'll give you the first question again. What do you look forward to at LSF, MM, that's on our agenda, or things that we should have put on the agenda that aren't?
Oh, what I usually look forward to at LSF is making someone else do all the work for whatever ideas come out of it.
Yeah.
That's a maintainer's job.
That's absolutely true.
You do the work, I take the credit.
All right, Trond, so a different question, an NFS question. How many people use NFS here? So how is PNFS going to change your life?
It will currently change my life by allowing me to get rid of the whole responsibility for it. No, PNFS has been a recurring theme at the LSF for the past it's only been running for 7 or 8 years, but pretty much at every one. And last year, I promised, that we would never again speak about it. I have kept my word this year, so far. And the reason I can do that is because, as far as we're concerned, the client shipped a year ago and is currently actually in GA in Rel 6.4. We're working on making that the case for more distributions. So I think the main way that it's going to change your life is you're not going to actually notice that as we sort of slip it past you into your data centers.
So, any questions from the audience? You have to be mean. I know it's been a long 3 days, but there's got to be some good questions to poke at people.
If you're going to start asking questions, we'll start asking questions of the audience.
Yeah. So I'll ask a different question.
Yeah.
Now that everything's virtual, and anyone can take this, and we have all these user-space file systems, user-space, block targets, why do we have to worry about kernel file systems and storage anymore? Why can't we all just retire to the beach?
That's a good idea.
Yeah.
Let's go.
If you can answer the question, how do you expect to talk to your storage target without using the kernel, then you might be entitled to do this. There is an infrastructure you can theoretically use for user-space device drivers, but it's not the most efficient one. And one of the things that we really have to do with in-kernel device drivers is actually try and make an efficient communication channel between whatever esoteric hardware sits at the end of the bus and whatever application wants to make use of it. Now, obviously, being a storage guy, I don't think we need to bother with this file system rubbish, but I would always anticipate that we do need stuff in the kernel for efficient device drivers. I presume one of the file system guys would have something different to say about that.
Well, the problem is that you can put stuff in user space, but then you've got the problem of having to copy things in and out of the kernel to get them to the block devices that are nice and efficient. So if you want to do things efficiently at the file system layer, you've still got the problem of it having to be in the kernel. So you're not copying it in and out. You don't have issues with daemons in user space, and Fuse is wonderful for toys. But when you're actually talking about moving gigabytes of data, terabytes of data, and so on, overhead matters and efficiency matters, and it's the same reason.
Okay, I'll dispute that one.
Oh, go on.
So there are at least 3 different cloud file systems I know of that are already using Fuse as the engine for transmitting data sort of through the layer. Admittedly,
That's the client side.
No, and on the server side. We have actually cheated slightly, so I know Max will be talking about it in a day's time.
Yeah.
We have patches that actually accelerate fuse, and all we care about is acceleration of the data transmission path. So we think, and as long as cloud storage systems are speaking in terms of large objects, which pretty much they are, which is machine images, we can actually get an almost 95% efficient data transfer path through the kernel. You're about to pick me up about the metadata. Oh no, you're about to tell me XFS did this 10 years ago.
No, I'm about to tell you that we're having problems with distributed/cloud file systems, all to do with small files. Lots and lots of small files, 50 million, 100 million, and so on.
We already answered that question. The answer to that question is don't do it.
Yeah, people still do it.
It's not on our file system.
Yeah. Yes. So when you tell someone don't do something, somebody else does it for you. Next.
Trond.
Well, I dispute that XFS did it 10 years ago, but Samba certainly did.
Yeah.
You know, they've been running as a user space file system for 15, 20 years now, and nobody's been complaining about that. So I don't think the concept of a user space file system is really that novel or revolutionary. You know, what's sort of special about what's coming up now is more the scale out features that people are starting to add in, which allows you to basically increase the bandwidth to your file system by putting more objects or storage units in front of your client and sort of splitting the networking bandwidth to them. So I'd say that the future is network file systems.
All right. So following up on that, Trond, you left yourself wide open. So SMB3, how does NFS 4.1, 4.2 compare to SMB 3.0 for Microsoft in terms of features and performance?
I cannot comment on the performance. I haven't seen any numbers. As far as features go, there are a few interesting features in SMB3 that I think we're interested in looking at. At least I personally am interested in looking at. Not least the ability to do proper write delegation of directories and subtrees. That's a really neat feature that allows you basically to, if you've got something like a temporary file that you basically just want the file system as a sort of backing for your memory, your page cache. You can basically keep that thing cached for as long as you still have memory for it, not write it out, maybe not even actually create an inode for it on the storage, and in all ways act like local file systems have done for years in these situations. Another sort of pet puppy of mine is the peer-to-peer features. I actually wrote a PNFS driver that does something like that and submitted it to the IETF 3 years ago that does something similar. And I'm currently working on a prototype for that.
So I don't think the peer-to-peer stuff is really technically part of SMB3. It's own entity. Oh, sorry.
Yeah.
The peer-to-peer stuff. The peer-to-peer stuff is not technically part of SMB3. I think it's its own beast that they do, but it is neat stuff. Yeah. Their branch cache stuff that they do, where they we can talk about it offline, but essentially they hash chunks of data that clients might on your network have, and then you can kind of go out and request for, does anybody have this chunk with this hash? And so it's a little bit
It's
like
a little
that,
bit like
actually.
BitTorrent,
So,
yeah. Dan, you had a question?
Okay. Say in the next 3 to 5 years, there's bound to be a lot of hardware changes at the CPU level, at the system level, maybe even at the data center topology level. What technology that you can either know today or expect might be evolving in the next few years do you expect to strike the most fear into your heart in your subsystem?
Shall I start?
Okay, sure.
Yeah, I actually see a very bright future for my particular file system, as technologies such as persistent memory, which has been the subject of several talks earlier today, basically increases the need for tiered file systems. In a few years, your laptop, is, it's already the case that most of them ship without any spinning media, flash. In a few more years, they'll have storage capabilities, which rival, if not match outright, the speed of DRAM. And when that happens, why even have a disk? Why even have a file system? And so, the interesting aspect is going to be sort of how do you get the data from my laptop to, Google's data center, or wherever it is that you store your large data, shared data.
All right, Mr. Jenner, do you still have a job in 3 years?
Quite possibly. The thing that worries me the most, well, we'll stay on persistent memory here, and I'll add one word to it: persistent memory corruption.
So I can't dispute Trond slightly in the no file system thing. The reason we have file systems is because when people dump data and they come back to it, they actually like it still to be there. They like to be able to still find it. If you just treat things as a memory array, the problem is you can't actually always find your data again.
You need a name.
You basically, a file system's job is name-to-data translation, and we'll still need to do that.
Yeah.
But at least from all the technologies you mentioned, a lot of the incremental innovations is acceleration technology, so things in the processor that make hypervisors or storage or other things work faster. There are a few sort of technologies that flip the world around, so things like SSDs send disks from sort of 1,000 to 10,000 IOPS up to sort of 100,000 to 1 million IOPS almost overnight, so things like that we have to cope with. And then at the data center level, most of the technological changes there are to do with sort of high-level virtualization functions that we don't have to care at all about inside the kernel. So things like software-defined networking, topology definitions, the odd clustering algorithm that, it still operates above the kernel. So I think in the realm that we care about, we've really mentioned most of the technologies we see in the pipe that are actually going to accelerate it. The most interesting thing for me about transactional memory is that if you're treating your storage as memory with a memory protocol, you don't really need a storage stack anymore. So I can just tick the job done box and disappear off into the sunset. And it becomes his problem.
Yeah, for me, there are several scary things with non-volatile memory as well. One of the main benefits of non-volatile memory is that it is extremely fast, and you can access it like normal memory. But that also means you can no longer have things like a block layer in between that memory and your application. At that point, you can no longer make snapshots of your data and make a backup that is consistent. You'll have a backup that has state from various times of your database, for example. And restoring that backup might not result in a functioning database. So the non-volatile memory still has a large issue with backups. A second issue related to this is today a lot of people use virtual machines because if a system crashes, they can simply start the virtual machine back up somewhere else. But if a lot of the data lives on the non-volatile memory of one particular system, the data is modified. It lives on non-volatile memory because it needs to be modified very, very rapidly. That means the data modification is going to be so fast, you cannot possibly mirror them on another system. And if a system fails, you will be unable to restart your virtual machine somewhere else. There are some real issues going on that we're going to have to think about, and maybe some of them need to be solved on the application level, because the operating system level can no longer handle it with the modern performance demands.
Yeah, and continuing down the road with applications, we have 20, 30 years of Unix applications that haven't quite figured out how to drive the Unix API to make the storage work well, and introducing a new programming model potentially into the mix is not going to make things easier. So there are definitely going to be some challenges in that department in terms of converting or completely re-engineering the way applications work to work well with a transactional memory system.
I'll give you a little bit of hope, Martin. I think it'll be a lot easier to tell application developers they don't need to f-sync anymore.
But what about msync?
msync. Yeah. Other questions in the audience? Yeah.
There's lots of talk about this non-volatile memory, but at some point, people are going to, certain companies are going to insist it being encrypted. So presumably they'll need offload encryption for this. How's this going to fit into everything?
Offload encryption is just a CPU function. We already have something like the Intel IOAT that can do in-flight compression and memory transformations. It's not too much of a stretch to have it do in-flight compression as well. So in theory, you should be able to just get a little chip in either the North Bridge or the South Bridge or the memory bus that will just do this for you, and you feed the key in. And then theoretically, you can shred your memory just by losing the key. So I don't... Well, the key is obviously stored in TP.
You write it down in the back of your hand. Yeah.
So I don't see that as being any barrier to the current models. Was there some policy question you were going to ask about? No, you were just how we do it. Okay, that's how we do it.
And I mean, encrypting the non-volatile memory is just a really tiny addition compared to all the other complicated stuff that you already have to do to take care of things like wire leveling and potentially remapping and transactions.
So I've got a question. I'm gonna start with Martin down at the other end of the line. So, assuming size matters, how big is storage going to be in a useful pool? How big is a single partition going to be? How big a file system needs to be? Anybody here use 4 terabyte file systems today? Production use? 100 terabytes? It's 3. In one file system, not distributed. Petabyte? Anybody hit a petabyte? You NASA guys? Yeah, Lester. Yeah, so we're always getting pressed to go bigger and bigger and bigger and bigger. How big is big enough?
I don't think I have a number for you, but I have a concern for you, and that is consistency checking, and the time it takes to do so. And I think that's still one of the main gating factors. As long as we're talking spinning storage, the fact that the IOPS are not really going up with capacity. So we have, in many cases, physical or memory limits that are gating the size of the file system rather than the actual capacity that we can physically hook up to the machine.
Yeah. I mean, effectively, FSCK, if it takes more than a couple hours, you go to your backup tapes. Right? Yeah. Same question for Rick. How much DRAM can you have in a box, Rick?
We're actually hitting interesting things there now, where the issue isn't as much how much DRAM you have in the system, but how long can you wait for your application to start up? If you have a server application that uses 4 terabytes of RAM, and the application starts up, starts accessing all of the memory, and it all gets zeroed out by the kernel, that could take a really, really long time for your application to start. Application exiting, if you need to restart it for whatever reason, could take quite a while too, because it's just a lot of memory to manipulate and to handle. And the latency involved with stopping and restarting applications is sometimes too high for people already without reaching the terabyte level.
So I'm going to ask a mean question. This is my favorite mean question for MM people. If you have a terabyte of DRAM in your laptop, can I get rid of my swap partition?
On your laptop, probably yes. But if it's a NUMA system with many nodes, we don't have a way yet in the kernel to move stuff from one NUMA node to another to alleviate memory pressure. And that's something that we probably should add at some point, because then you would be able to get rid of your swap partition.
Yeah, just on swap, I know that almost the entirety of the Googleplex runs without swap. They really hate it, right? So losing swap is one of the things that a lot of enterprise-level applications are already thinking about doing. Okay, hand us the mic.
Turn it on.
Right. Okay. Another problem which we are hitting currently is it's nice that you can put in, say, 2 terabytes of memory into your machine, but waiting for that machine to dump is, in most cases, exceeding the any window you might have. And you might obviously have to reserve enough space for you to be even able to dump.
But I think all of these problems are classified as the sort of river and reservoir problem. The capacity of the reservoir is growing far faster than the capacity of the river to feed it. And so we're having trouble sort of getting the water in and getting the water out. Same for memory, same for storage, same for everything else. And at some point, this is a problem we are going to have to address. The pipes are not growing at the same size as the capacity is.
That'll help.
But then you have the problem with how to generate that much data in time. That you can
More CPUs. Yeah. So the problem with, for example, file systems and repair time and so on, one of the approaches we're taking to reduce that problem is to move more towards an online scrubbing consistency checking that happens in the background. Rather than, oh, something failed, now we have to run repair and now we need a couple of terabytes of RAM and so on to repair our petabyte file system. We're consistently checking it in the background. There's information being put on disk to make metadata self-describing, self-validating with back pointers, back references. Btrfs is doing this sort of thing. I'm almost at the point where we've got the information on disk for XFS to do similar things. It is the problem with scaling file systems that it's the repair time, and so we have to look at other ways of solving that problem.
I've got a mean question for you when you're done.
Yeah, okay. So effectively what we're trying to do is look at correcting errors at the point in time they occur, being able to handle the errors, detect, robust detection, being able to isolate faults to small parts of file systems, and so being able to have enough information to be able to reconstruct what was supposed to be there. If we don't do that, then we fall back to needing to do an offline repair, and then that's a black hole that causes your world to explode.
And even just identifying what you lost, even if you can't reconstruct, if you can just say this file is no longer there, but everything else is good.
Okay, so here's the main question first.
Ted wanted to follow up as well.
Yeah, so there's... Are we on here?
Green light on the side? Yeah.
There we go. So there's one interesting thing I've been noticing. People are talking about, putting large amounts of space onto a single file system and talking about the repair time, but I haven't noticed anyone talking about the robustness and reliability problem, which is if you have a single point of failure, 1 petabyte hooked up to a single server and the server dies, you've just lost access to that entire petabyte of data. If it's connected over fiber channel, you have to worry about RAID controllers or your fiber channel connector being your single point of failure. And so there's a question of if you don't need scale up, maybe the right answer really is scale out and cluster file systems.
So to answer that, yes, scale out is one answer. But what we're seeing, even go back 3 or 4 years ago, I was hearing about people using, XFS for, back-end object storage of scale-out systems, and they were talking about having 20 petabytes of storage in about 50 servers. and they were replicating and so on across it. The thing is that the individual XFS file systems were in the order of several hundred terabytes, and they were over tens of machines. So even when you start to talk about scale out, there is still some level of scale up that is occurring within the nodes. And if we look at the rate at which disks are growing, I mean, just look at, we've got 4 terabyte drives right now. You can easily put 50 terabytes of disk space in a 2-unit rack mount system, easy. In 5 years' time, that's going to be more like, 200, 300 terabytes of space in that same physical enclosure. So we're going to still see some level of scale up within each node in a scale out cluster, and so we still have to deal with this particular problem, no matter how you look at it.
Not necessarily. You could just simply have, if you have 20 different spindles, you can have 20 different independent file systems that are attached to that server that is part of the cloud file system, assuming that your cloud file system can handle that, right? So that's assuming you have a cloud file system that is designed to scale to that many spindles.
Yeah, sure, but the other thing there is that when you've got 20 terabytes behind a single spindle and you still only got 200 IOPS, repair on that single spindle is a significant problem. It's exactly the same problem we have right now with 2 terabytes and a single spindle, or 100 terabytes and a couple of spindles.
Yeah, I mean, there's sort of a general problem there of seek constraints and why we need flash, right? But that's a separate question.
And I think, Ted, another thing you see if you actually do mount dozens or hundreds of file systems per node is you could have memory pressure from things like the journal, right? If you have 100 active file systems all pounding, you get into other weird scalability issues.
Okay, so that wasn't...
Yeah, well, if you have that many servers and you have to be robust against, entry racks failures or motherboard failures or power supply failures, your cluster file system is going to have redundancy such that you may not need journals at all. I mean, there's a reason why ext4 has no journal mode.
So my main question was about the mean time between failures, because that's not rising at the same rate as the capacity of disks is rising. And what that means is that even if you write data at your bus speed, which is rising, or you use a fraction of your disk, which is rising, the more the chances of failure are actually going up in that. And if you engage in activities like online scrubbing that continually scan the data and reread it, you're also increasing the chance you'll actually precipitate the failure you're actually checking against. What are you doing to mitigate that problem?
Well, first of all, I'll point out that media scrubbing done in RAID arrays actually improves the reliability of the drives, because you're proactively detecting failures and potentially sectors on disk that are on the edge of failure before they actually fail. So similar sort of thing. While the actual amount of work you're doing and the bandwidth you're pulling off the disks is increasing, by actually going and accessing that data, you're actually improving the statistical probability that you'll find an error before it becomes fatal. And that's basically the basis behind it. You have to be proactive when you're talking about avoiding having to scan every single bit in the file system to determine what's gone wrong. There is some level of trade-off there. There's additional complexity in the software. There's additional bandwidth required through the file system, the hardware. But the trade-off is that we can detect errors before they become fatal and require you to shut everything down and spend days, even weeks, trying to recover from a failure.
Yeah. So the bottom line is we have to be more proactive about error detection and recovery, and this means that the storage layer has to speak to the file system layer, has to speak to the application layer when things go wrong.
Yep.
And we'll be talking about that in the next couple of days.
Yes.
Oh no, we don't care about that.
Anybody else?
Why don't we just leave that switched on?
Yes, on. So all the back-end devices support lots of concurrency, right? Especially SSDs. So you've got to have lots of threads going in order to really hit the peak IOPS. So from a maintenance point of view, we talked about file system checks and things like that. So what's the prospects going forward of, taking advantage of some of that parallelism in doing consistency checks or other things that you do in terms of maintaining a file system or recovering from issues?
We've already parallelized XFS repair, for example, and you can basically drive an arbitrary amount of parallelism through the repair process, as much as the underlying storage subsystem can handle. So we can max out either bandwidth or IOPS, depending on which one and which phase of repair we're actually running through. I've seen repair pull gigabyte second of metadata off disk in doing a repair of a large file system. So that sort of problem, that sort of approach to solving the scalability problem has brought us already over an order of magnitude improvement in repair times. So even having done that, we still have issues with, we might be able to read a gigabyte of metadata a second, but when you've got a billion inodes in the file system and you're talking about terabytes of metadata, that's still an awful long time for your file system to be down when you've got to meet a 5 nines SLA. You just can't do it. That's really what it comes down to. And as things get bigger and bigger and we get more and more parallelization, we'll max out the underlying storage without any problems at all, and it will still take days to run a repair.
More questions? One in the back there.
I'm one of these evil guys that mess around in PNFS. I just didn't get out of the way in time. An interesting bit, and we've been talking about larger and larger file systems around essentially single nodes. And we've got one of our contributors who runs large clusters. And he doesn't tell me a lot of detail, but they are going to smaller and smaller and cheaper compute nodes, which also translates into smaller memory, which is why there's an interest in 9P, because it's a lighter weight protocol. Now, whether any of us in the room are going to agree with that is being true. We'll leave that for later. But there is a trend on the client side where they're getting smaller and smaller and more of them to do the same amount of work. And so I'm starting to get concerned about just swamping the server. The same amount of computes on the other end of the line. The trouble is it's not 10,000 nodes in a cluster anymore. It's 200,000. And all of a sudden a lot of stacks start getting a little weird and start exploding. So that's, I don't know, it's going to be in the next year or so, but I hear that train coming.
That was a comment.
That was a comment.
If you guys want to add something to it from what you've been seeing, I hear that train coming. Do you hear it too?
Yeah.
Our response has been to get rid of NFSv2.
Yeah, I think also...
We did.
Yeah.
We did. Most of our response has been to enable the people who know what they're doing in this area to actually do it well. Actually, I hesitate now, I said know what I'm doing to mention cloud in the same breath, but there are a lot of people considering that exact scale-out problem. And our job in the kernel is to add the correct interfaces that make scale-out possible, and we're looking at that.
Yeah, another thing to consider is that 5 years from now, those small servers will still be 12 or 16 cores and have a terabyte or more of memory.
Yeah, but there'll be 200,000 of them.
Yeah.
Yeah.
All for $99.
Yeah. So there's another question? Yeah.
Yeah, I have a question about the memory management coherency. You just mentioned, when you do the file checkup and the CPU try to write into that memory, so it will cause the checkup fail. So what's the current solution for the memory coherency?
The current solution for that is to not allow writes to a page while I/O on that page is underway. It's called stable pages.
So use the software to do the page granularity protection, right?
Yes, the granularity is per page, I believe.
Per page. Okay, thank you.
Okay, I'm going to ask a question to help out John, since John and LWN have dutifully done the weather report for us for many, many, many years, giving us a view into the future. So what features, when Linus opens the window for the 310 merge window at the most inconvenient time, which will be like tomorrow morning as we kick off LSF, what features are each of you going to be pushing that John was going to be talking about at the next collab or LinuxCon?
I will not be pushing the copy file offload tomorrow.
I'm hoping Ingo will push the scheduling part of the automatic NUMA placement code.
All I've got is basically incremental updates to a ton of drivers, the usual stuff. I think there's an LPFC one, a QLA2X one, a QLA4X one, but none of them is enabling any of... I think the only controversial feature that is still not in my tree is the FNIC VLAN feature, which I was actually waiting for the network guys to comment on.
I'm kind of hoping that Ben will get to pushing the self-describing metadata changes for XFS upstream.
We're basically in the process of finishing off PNFS, so there won't be much in the way of new features. What I was hoping to be able to push was actually some patches that Red Hat have been writing to add SE Linux support.
So the labeled NFS.
Labeled NFS support to the client. Unfortunately, it looks more like a 3.11 job at this point.
Anything in the audience from the other kernel people? Any major features pending?
Yeah, if we didn't mention your patch, now would be the time to say.
Yeah.
I still have the 6 for Bitboom.
I want you to sort out the legacy addressing mode for that before I put it upstream.
Already done.
Okay, I'll have a look at it.
No, it's,
There is a
controversial case because we are already doing, strictly speaking, having an error in the stack now. Sequential scan. Sequential scan beyond 256 lines.
It's completely pointless. Almost everything that does beyond 256 lines does report lines.
No, it's not only point, it's wrong. Because it's not defined. Unless you happen to run a SCSI-3 array, which I hope doesn't exist. But for everything other than SCSI-3, it's illegal.
No, we have the flag. You put the flag in.
All right.
Right, whatever.
You guys can discuss it over drinks in an hour. Yeah. So one in the back.
Yeah.
Oh, I just wanted to say that this isn't a 3.10 thing, but when 3.9 comes out, stable pages will suck somewhat less.
Other features? Nobody in the audience who's not a kernel developer has features you want us to do?
It's in next. I don't know if it will end up in 3.10, but it's in next right now.
I think we've talked them into the ground.
Doesn't anybody want to flame us?
We're all doing a perfect job. You can just say thank you.
Thank you.
Any of your data is here.
I actually just have a question.
And I'm sorry to interrupt all the storage talk, but I actually had a question for Rick based on his earlier comment about offloading to the GPU and the implications as far as memory coherency on that. And it relates also to, it seems that as single system images are scaling up, the cache coherency logic in the firmware is becoming major bottlenecks and a major problem, you know, both in the hardware layer and for the OS to work around the issues. And so that raised the question in my mind, do you, and you know, part of this is asking you to read the tea leaves and predict the future, as I'm sure you do so well. Do you think the trend will be to move to perhaps a NUMA topology where we actually have cache coherency domains instead of just latency domains? And if so, do you see the GPU work playing into that, where, you know, we could actually architect the OS to, you know, basically do either, you know, replication and task passage between the cache coherency domains such that we don't have to worry about the actual, you know, address spaces overlapping directly, but can shuttle work quickly through a fast internal bus kind of layout.
And I just, before you even answer, I want to say, if anyone's ever suspected Collab Summit doesn't have room for technical questions.
I'm sorry, was that too bad?
It's while the infrastructure that we're talking about for coprocessor use should be usable for a system like you describe, it's also worth remembering that this infrastructure is being introduced because CPUs are no longer the fastest out there. And that makes me wonder what the future of scale-up is going to be, if it is going to be around CPUs at all, or if people who want to do lots of compute on a system will have a bunch of coprocessors sitting in the system and not general-purpose CPUs to do the bulk of the calculations.
Rick, I just want to respond to that by pointing out that a modern GPU actually consists of CPUs these days.
Pretty much, yes. Just smaller, specialized ones that you wouldn't want to run a kernel on them, but you might have 800 of them that do certain tasks really, really quickly.
But will you need to run a micro section of the kernel on them in order to handle the coherency? You know, I mean, are we basically talking about carving up bits of kernel functionality and replicating it across, you know, the coprocessors or the coherency domains or whatever we want to call it?
Yeah. Grab a mic pick there. Yeah.
I'll grab this mic. The thing is, someone tried to do that before. Like very large, globally shared memory machines were tried in the 90s and 2000s, and maintaining global coherency on that level just completely falls apart. It leads for an easy programming model, but it generally doesn't work. I would expect, I at least would expect that any accelerator orientated cluster would not try and maintain global coherency. It would only maintain coherency between the CPU consuming the result of the accelerator, whatever the accelerator did. I would only expect coherency to be managed there. So your question is like, how will we manage global coherency? I would think we just won't.
Actually, more assuming that we can't handle global coherency across. You know, we can't fake up a true physical global address space because of the coherency issues. How would we leverage the infrastructure that would result from that?
Well,
as far as, you know,
we can fake up a large global system. It's just going to be slower.
Well, yeah, okay. I'm sorry. Can is a relative thing. I didn't mean can as in it's technically impossible, but can as in it wouldn't be performant. So.
Yeah, and that's really what it's all about. You want to be able to easily pass data off to your offload coprocessors and get it back into the program that's consuming it. But beyond that, the kernel probably does not need to run on the coprocessors at all. It could run on your main CPUs. And the other compute engines could run only the calculations that you want them to run.
Yeah, supercomputers did this years ago, right? Different
There's current supercomputers that do this.
Yeah. I think that's a great discussion over drinks in about 30 minutes. Any other questions, the audience? Good. Yep. You can borrow our mic. Yeah. Yeah.
Sure. So this week, in fact, we've got a bunch of pile of storage showing up. It's going to be about 5 petabytes of storage. And so it'll be behind 30 servers and a bunch of NetApp boxes, right? So, and of course we're going to install Lustre, and so we're probably 1 or 2 file systems at the most. And so we have this issue, right, of checking file systems and ensuring coherency or consistency across it, dealing with hardware issues and failures. And so that's what we're going to do today, but, you know, what are you guys going to do for us in the future to make that easy, right? So we really want, you know, I think going forward, more and more you're going to see, you know, this distributed aspect is just going to, you know, go everywhere, right? Everybody's going to want to have more than a single server on the back end. And so a tiered, you know, right now our file systems have file systems, basically, right? That's how it's implemented. And so it's almost like the secondary file system is a block device layer that's manipulated from the file system that sits on the front ends. So what would you predict, I guess, going forward, how you're going to solve that sort of problem in the future?
No, that wasn't what I was going to say. In a way, the problem that you're talking about is really, once again, the scale-out problem. And that's what distributed file systems are actually trying to solve. As I was saying earlier, that there is still a level of scale-up that occurs, and you're definitely in the scale-up and then scale-out type of situation. So, I mean, I'm not sure that it's really anything more than what we've already talked about that we can do to address the problems that you're seeing right now. I mean, HPC is well known to be way out in the lunatic fringe, and we do what we can for lunatics. But I think that you know, when we're looking at this sort of scale, the only way to go from where you are now to where you want to be is to scale out further. There are going to be limits of what we can do in terms of scale up. So it's just going to have to scale out.
And I think a big part of what we're going to do for you is hopefully make it easier to manage those boxes. I mean, as you get dozens and hundreds and thousands of nodes, Linux boxes aren't as easy to manage as they could be.
Actually, there are 2 points to your question. One is the scale-out one that David addressed, but the other one is the endpoint problem. So if technology is getting more like non-volatile DRAM, where there's only a single endpoint for your data, then that just doesn't fit into a scale-out world. Whereas if technology gets to the point where you can actually address multiple endpoints for everything, then that does fit into your scale-out world. And so we're also going to have to reconcile the desire for the industry to do one-to-one, which is why DRAM, non-volatile DRAM, is a lot faster storage than something that has to use a boring protocol that's encapsulated and goes over a bus, each of those points introducing latency, and the desire of the industry just to get data back as fast as possible. And so we'll sit on the edge of that, but we implement what the industry does effectively, so whichever way it blows is the way that we'll eventually implement the interfaces. Anybody else?
I think that's a perfect. We're at 5:30. Unless there's any pressing questions for everybody, we can let you all escape. Thank you.